You've seen what AI can do, right? Models like ChatGPT can write poetry, they can code, they can explain incredibly complex science. Honestly, it feels like magic, like there's a real mind inside the machine. But what if the secret behind all of it is actually shockingly simple? Today, we're going to pull back that curtain, and with a little help from two top researchers at OpenAI, we're going to figure out how this all really works.
So here's how we're going to break this all down. We're going to start with the one simple task at the absolute heart of AI. Then we'll look at the wild effects of just doing more of it, of scale. We'll unpack this thing called the bitter lesson of AI research, and finally, see what's really driving this whole revolution forward.
You'd think, right, that to build something so powerful, you'd need this incredibly complex set of instructions. But nope. The entire foundation of these massive models, it all comes down to one single core task. And when you first hear it, it sounds almost boring.
Okay, so as OpenAI researcher Jason Wei puts it, it's literally this simple. You give the model a phrase like, Dartmouth students like to, and its entire job is to guess the next word. It might say, study has a 30% chance, and drink has a 60% chance. Then you show it the correct answer, and it learns. It just adjusts itself. Now here's the key. Imagine doing that trillions of times with pretty much all the text on the internet. But see, this simple task is kind of a Trojan horse. To get really good at predicting the next word, the model can't just memorize stuff. It's forced to actually learn millions of other little skills, has to understand grammar, has to learn facts about the world, and even has to figure out translation and basic reasoning. We call this massively multitask learning, and it all happens automatically, just from trying to guess the next word.
All right, so the foundation is one simple task. The next crucial ingredient is what happens when you apply an almost unimaginable amount of scale to it. And this is where things start to get really weird and really interesting.
Researchers discovered something so consistent, so predictable, that they actually call it a law, the scaling law. It basically says that as you pump in more compute, which just means more data and bigger models, the model's overall performance gets better. Not just a little better, and not in a messy, unpredictable way. It gets smoothly and reliably better, across 7 orders of magnitude. The performance curve just keeps going down, like clockwork.
But, and this is a huge but, here's the fascinating twist. While the overall performance improves smoothly, the performance on individual skills does not at all. Jason Wei and his team studied over 200 different tasks, and they found that about a third of all the abilities, they didn't get gradually better. They just appeared, out of nowhere.
This sudden appearance of skills is a critical concept. It's the thing that really explains that feeling of magic people get when they use these huge, powerful AI models for the first time.
What this means is you could test a small model on, say, multi-digit arithmetic, and it would completely fail. Its performance would be 0. You'd naturally think, okay, this kind of model just can't do math. But then, you train a slightly larger model, and all of a sudden, it can. It's not a gradual improvement. It goes from nothing to something just like that. This unpredictability, it's a core feature of scaling.
So this whole phenomenon isn't just some random accident. According to another OpenAI researcher, Hyung Won Chung, it's actually the result of a core philosophy in AI that's been proving itself right again and again for decades.
It's known as the bitter lesson. And it's called bitter because for 70 years, brilliant researchers tried to build clever, complex systems by handcrafting human knowledge and assumptions right into them. But time and time again, the methods that end up winning are the simple, general ones that can just soak up more and more raw computer power.
And this lays out the fundamental trade-off perfectly. When you bake in a lot of human-designed structure, you get a short-term win. Your model learns faster right out of the gate. But that very same structure eventually becomes a bottleneck. It creates a ceiling that the model just can't break through. Simpler, more general models? Well, they might learn a bit slower at first, but because they have fewer built-in constraints, they have no ceiling. They just keep getting better and better with more scale.
And you know, we can see this exact principle in action if we look at the transformer itself. That's the architecture that powers all these models. Over the years, researchers have actually been making it simpler, not more complicated.
As Chung explains, the original transformer from back in 2017 was actually more complex. It had a separate part, an encoder for the input text, and another part, a decoder for the output. It assumed they were different things. But modern models, like GPT, they use a much simpler decoder-only architecture. It just treats everything, input and output, as one long, continuous sequence.
It removes the old assumptions, which makes it more general and way more scalable. Okay, so if the recipe is a super simple task and a super simple architecture, what's the actual engine that's making all of this possible? What's the one unstoppable trend that researchers are tapping into?
Chung points to this one single dominant force that has been shaping AI for over a century: exponentially cheaper compute. Every 5 years, for the same amount of money, you can buy 10 times more computing power. This trend is so powerful, he argues, you just can't compete with it. It's like trying to fight gravity. So you have to build methods that don't just use it, but leverage it.
And so, this brings us to the full recipe for modern AI. You see, it's not about designing complexity into the system from the very beginning. It's about creating the absolute simplest possible conditions and then hooking it up to a massive engine of data and compute and just letting complexity emerge all on its own.
So, what does this all mean for the future? I mean, if the main driver here isn't some clever new human insight, but instead this unstoppable economic and technological trend, well, the implications are pretty profound.
I think the really big takeaway here is that future progress in AI might be less about us waiting for the next genius algorithm and more about just riding this exponential wave of computation. The most incredible breakthroughs might not be designed by a person, but will simply emerge, waiting for us at the next orders of magnitude and scale. The real question is, what abilities will appear then?